Okay guys, welcome to Physics 203 Class 19. This video is about applying the quantum mechanics to the hydrogen atom. And we've seen that the hydrogen atom has been a very important system for understanding the transition from classical to quantum physics and now to quantum mechanics. It's a very natural system in that it's simple. It has a proton and an electron and just one interaction. So although the math can still get, as you'll see, can still get a little complicated, and it took physicists a while to get a handle on it, it's a natural testing ground for quantum physics. So let's review a little bit of what we've seen of the hydrogen atom. If you recall, there were mysterious spectral lines of hydrogen in the visible spectrum. And when you passed a hydrogen lamp, excited hydrogen lamp through a prism, it separated into red and blue and violet lines, blue-green lines. It wasn't understood how these lines were determined. And if you remember, it was Balmer, a Swiss school teacher, who just came up with this formula kind of out of the blue, which where n final was 2 and n initial could be 3, 4, 5, or 6, and r was this value. It could predict these measured wavelengths exactly. So, and then the Balmer formula, which was mysterious for a while, was finally given a justification by Niels Bohr and Louis de Broglie in beginning of quantum theory in the 1910s and early 1920s. Niels Bohr, if you remember, with the Bohr model, he postulated that, well, he had 4 postulates, but 2 of them were that the angular momentum was equal to integer multiples of h bar, where h bar is h over 2 pi, the Planck's constant, and that the emitted photons of light were equal to the final energy of the photon minus the initial energy of the photon, and that was related to the frequency and the wave, therefore the wavelength, by the energy of the photon being equal to hf, as in the photoelectric effect and blackbody radiation. And then Louis de Broglie came along and gave a justification for this quantization of angular momentum. He said that, as you remember, hopefully, an electron has wave-like properties, and when the electron fit an even number of times, or an integral number of times around the orbit, that was an allowed orbit. And from that condition, we could derive Bohr's postulate here. Okay, so the hydrogen atom had a rich history, and we'll see that, and as I said in the introduction, it has only one electrical interaction between the central proton and the nucleus and the electron. Now let's apply the time-independent Schrödinger equation, which we've applied so far to the infinite one-dimensional square well, and the barrier and the barrier potential, basically. And let's apply that to the hydrogen atom. Now, the biggest difference here is that the hydrogen atom is 3-dimensional, whereas the barrier potentials and the one-dimensional infinite square well were 1-dimensional. So our equation is going to be a little bit more involved. So we're going to be dealing with a 3-dimensional TISE, or time-independent Schrödinger equation. And so here's the nucleus, and here's the electron, just a rendition of them. They're separated by a distance r. And remember that the interaction is minus ke squared over r, or where k can be written as 1 over 4 pi epsilon naught. So the three-dimensional Coulomb interaction, though, depends only on the distance r. Okay, it doesn't depend on the angle that the electron is at. It's only on the distance r away, and this is the potential energy. So how do we go from 1 to 3 dimensions? Well, if you imagine blocking out these two terms right here, this y term and this z term, if you just block those out, then what's left, minus h bar squared over 2m second derivative of psi squared plus v psi equal e psi, that's the time-independent Schrodinger equation for 1 dimension. In Cartesian coordinates, we just add a term for the second derivative with respect to y and the second derivative with respect to z. So that's pretty much as what you might guess, and as simple as possible. Okay, but Cartesian coordinates aren't that convenient for the hydrogen atom because of this dependence on r. Which is not x, y, or z. R is a combination of x, y, and z. So it's better to move to spherical coordinates, and we can actually transform this equation, these derivatives in here, from derivatives with respect to x, y, and z to derivatives with respect to the spherical coordinates r, theta, and phi. And you'll see the mechanics of doing that in among other courses, Physics 350, the electrodynamics course. But if we do that, that procedure, and we rearrange the equation, and instead of the mass, we use the reduced mass, which takes into account the fact that the proton and the electron rotate around a common center of mass rather than the center of the proton, we get this equation here. Okay, which as you can see is 7.3 in your textbook. It's a pretty massive equation. There's no denying that. But you can see that if we take, you can see what's going on here. We have E minus V, okay, times psi, so that comes from subtracting V here. And then multiplying by 2m or mu, the reduced mass over h bar squared, gives this term. And then this stuff here, when we transform from Cartesian to spherical coordinates, just turns out to give this expression here, okay? And again, we're just going to accept that as a given. And you're not going to have to, memorize or solve this equation, but just be aware that this is the spherical version of the sum of the partial derivatives in Cartesian coordinates. Okay, so again, why are we doing this? It's best written for the hydrogen atom in spherical as Cartesian coordinates to take advantage of the form, the symmetry of the Coulomb interaction, which only depends on the distance r, so it's symmetric with respect to all the angles. Again, looks complicated, but to break down the complication, we apply separation of variables. So we write the solution in separation of variables of the spherical coordinates r, theta, and phi as a function of r alone, which we'll call capital R, and a function of theta alone, which we'll call capital F, and a function of phi alone, which we'll call G. And so we'll try this to plug in this form for psi and see if we can make some progress on this equation. And in fact, we can. And this is, we've used separation of variables before. That's what we used when we broke the time-dependent Schrodinger equation into the time-independent Schrodinger equation and the exponential time dependence. Okay, back a few videos ago or lectures ago. It's the same idea here, breaking a complicated problem down and assuming this multiplying form, and that makes things manageable. Okay, so let's see how the separation of variables works, and review the meaning of the separation of variables, what the technique does. So if we take this assumed form for the separation of variables for the wave function psi and substitute into that equation on the previous slide and rearrange, And you can check your textbook for some intermediate steps here around equation 7.3 if you'd like. But we get this equation here, where, again, capital R is the radial function, F is the angular function, and G is called the azimuthal function. And okay, so again, looks like a complicated equation, but notice a couple things, or notice one particular thing. The left-hand side here, the whole left-hand side, depends only on theta and R, okay? You only see R's and thetas appearing over here. Okay, and F's, but F depends only on theta. So, whereas on the right side, it only depends on the azimuthal angle phi, because G depends on phi, and we have the second derivative of phi squared. So if this is going to be true for all values of R and theta, and all values of phi, the only way that can happen, because both sides will vary as R and theta are varied and as phi is varied, if both sides are equal to the same constant. Okay, so that's the idea of separation of variables. We get one, or in this case, two variables on one side and a variable on the other side. We recognize that they can vary independently, and so they must both be equal to a common or the same constant. So here we choose this constant to be, you might just say, why don't we choose the constant to be k or something like that, but we choose it to be minus m sub l squared. And that seems a little mysterious, but the reason for this is just in retrospect, after you work through everything, you realize that this puts the solutions into the most convenient form if you choose this constant to be minus ml squared. So if you know the form of the equation that's coming up, so looking at the right-hand side and setting it equal to minus ml squared, our constant from separation of variables, we get, just multiplying through by g, the second derivative of g with respect to phi is equal to minus ml squared g, okay? And that's the azimuthal equation. And this has sinusoidal type solutions, okay? Sines, cosines, or imaginary exponential type solutions. It's of the form of the harmonic oscillator from Physics 201 and 202. So the solution we choose is the exponential solution, the imaginary exponential solution. And you might just want to try plugging in this solution to this equation here, that is taking two derivatives of this, taking two derivatives and showing that you get minus ml squared times this solution back again, just to fix these ideas for you. But anyway, since it turns out, since the wave function, one of the requirements on the wave function is it must be single valued, that is, at a given point in space, it should only have one value, not multiple values. That just seems like almost inconceivable that couldn't be the case. This gives, so the g at phi equals 0 must be the same as if we wrap around all the way to phi equals 2 pi, because that corresponds to going all the way around the azimuthal direction. Okay, so if we apply that to this e to the I ml phi, we get e to the, as the solution g, we get e to the I 0, e to the I ml times 0, which is e to the 0, and that's supposed to be equal to e to the I ml times 2 pi. So we get this condition. So this is saying e to the 0 or 1 is equal to e to the 2 pi I ml. Excuse me. So e to the 2 pi I ml goes around the complex plane, and it only returns to 1 when ml is an integer. An integer meaning positive 1, 2, 3, 4, negative 1, 2, 3, 4, etc., or 0. Okay. So again, we have a situation just like in the 1D infinite square well, where the boundary conditions in that case, it was the value of the wave function at the sides of the potential going to 0, or the required property of the wave function here that it's single valued, leading to a restricted so-called quantum number. Okay, and the quantum number here is m sub l. Okay, m sub l. So you can see why we chose m sub l squared here, because then we just got m sub l as the quantum number instead of like the square root of k or something like that. Okay, so there'll be more on quantum numbers next time, but this is the first quantum number we get for the hydrogen atom. It's called the azimuthal quantum number. Okay, now we're not done yet. We can do more separation of variables and find the form of the radial and angular functions. So a second separation of variables, which is in the textbook, which I won't show here, gives us equations for the radial function r and the angular function f. Okay, so I'll just present the results, and the radial equation looks like this. It's got some derivatives of the radial here, and the energy in here, and the Coulomb potential here, and then it's got this separation constant L times L plus 1. This is another case where it's chosen after the fact to give convenient expressions for quantities. So so that's the radial equation, and it's an equation which had been studied before quantum mechanics. The solutions to this are called associated Laguerre functions. Okay, and if you take physics 490, quantum mechanics, you'll study these in detail. But here we'll just kind of survey them. They have to go to 0, these r sub r, as r goes to infinity, because if they don't, that means the wave function will not go to 0 at infinity, and it will blow. Therefore, it won't be able to be normalized to have total probability 1. It turns out this leads in the process of solution to a quantum number n, the fact that r must go to big R must go to 0 as little r goes to infinity, with values n equal 1, 2, 3, 4. But notice that the function r depends on both the quantum number n and on this quantum number L, which appears as L times L plus 1. So here's just the first 3 sample radial functions. So n goes 1, 2, and then there would be 3, 4, 5, 6, and so forth. L can be 0, 1, 2, 3, and so forth. Now there are restrictions depending on the value of n, what the value of L can be, but we'll talk about those in the next lecture. So what does R look like? Notice it's indexed by n and L because it depends on both those quantum numbers. So the first one is just a decaying exponential function. The second one is a polynomial, a first order polynomial in R times a decaying exponential. The third one is another polynomial in R times a decaying exponential. And that's basically the type of form of solutions you'd get for the radial function. It'll be some polynomial times a decaying exponential. And the decaying exponential makes sure that R goes to 0 as big R goes to 0 as little r goes to infinity, because that's going to drop off fast. Okay, the angular equation, which comes out of this separation of variables, looks like this. Again, it involves this new quantum number L. It also involves the previous quantum number ml squared, it turns out. And so when you solve those, the solutions to those, F, are called associated Legendre functions. So we have Laguerre and Legendre, 2 famous French mathematicians. The boundary conditions on F lead to restricted values on the quantum number L. As I said, it can be 0, 1, 2, 3, 4, 5, 6, etc. Okay, so usually it's these are written, the angular dependence is combined with the azimuthal dependence into a composite function, which is usually written as a y, as a function of theta and phi, which would be f times g. And that's known, those are called spherical harmonics. They depend on the L and ML quantum numbers because you can see this equation here has L and ML in it. So here's some sample spherical harmonics. We can see that for L equals 0, ML equals 0, we just get a constant. So it's just a constant with respect to theta and phi, so that would just be plotted as it's a constant, so that would just be a sphere with radius, actually here 1/2 square root of pi. For L equal 1, ML equals 0, we get, it turns out, cosine theta. Here's that shown here, cosine theta for theta equal 0, which is up here, cosine theta equal 1, so that's big. As theta goes to down here to pi/2, the value of the function goes to 0, and then as theta increases again to pi, it goes to cosine theta goes to -1. Okay, so it goes down here to -1. Okay, so so these are the spherical harmonics, and they get more. You can look in the table. I've just as the top of the first 3 of the table in the book. They get more and more complicated, but in principle, they're just functions. These are functions of R, which depend on the quantum numbers n and L, and these are functions of theta and phi, which depend on the quantum numbers L and m sub L. So how do we get the full solution, psi? Well, remember, we said that it was equal to, by the separation of variables, R times F times G. But F times G is our spherical harmonic Y. So we can say that psi would be equal to R, which depends on these quantum number n and L, which is a function of the radius R, times Y, which is a function of theta and phi, and depends on the quantum numbers L and ML. So together, the wave function depends on 3 quantum numbers, n, L, and m sub L. N, L, and m sub L. And that makes sense because there's usually 1 quantum number for each dimension here, and we're dealing with 3 dimensions here as opposed to 1 dimension in the one-dimensional infinite square well, which we studied quite a lot. So these are just a couple of plots for of psi for n equals 2, L equals 0, m equals 0. So with L and m equal to 0, that's y 0, 0. So that would be just a constant. So this is spherically symmetric. It doesn't vary with either angle. But the R function is 2, 0, n equal 2, L equals 0. So if we look up here at 2, 0, we get a polynomial times the exponential. And so what that has the effect of concentrating a lot of wave function in the center, and then there's a gap here where there's very little wave function, very little probability for the electron to be found, and then the wave function falls off from there. For the other one, for n equal 2, L equal 1, m equals 0, well, let's look at L and m sub L. That's the cosine theta. So you can see this looks just similar to what we talked about before in terms of the angular dependence. It's got these 2 lobes. And then n equals 2, L equal 1, so 2, 1 goes as r to e to the minus r over 2 theta. So it goes it doesn't have this gap here, but it goes up through a maximum and then decreases down and falls off exponentially. Okay? All right, so last slide. We can get some physical insight. I know there's a lot of mathematics here, and but we can get some physical insight and connection to the Bohr model by looking at the L equals 0, the L equals 0 radial equation. So this is the radial equation. If we set the quantum number L equal to 0, this term disappears, and we get this. So it's just this over here written with this term gone, okay, if you look at it. And then if we evaluate these derivatives using the chain rule and break this up into two terms, we get this. So this is this equation, this expression and this expression are the same. And we substitute in the form of the Coulomb potential minus e squared over 4 pi epsilon naught r, which becomes minus of a minus, which becomes plus. We get an equation here for r. Now we can, it's a differential equation, so we can just, we're free to guess solutions. So from experience, if you work with differential equations, this looks like something that might involve exponentials. So we try the exponential solution. R is equal to a constant times e to the minus little r over a constant a naught. And if you do that, if you plug that in and go through some math, which you can find in your textbook if you want to see the intermediate steps, you get this following condition. This expression here involving a naught and mu and h bar and e, plus this expression here involving the same terms except for also the elementary charge and epsilon naught, times 1 over r is equal to 0. Okay? Okay, well, so what? Well, if you think about it, if this is always going to be equal to 0, and this term depends on r, if r can be anything, the only way this whole thing can always be equal to 0 is if both this term in parentheses and this term in parentheses are each 0. So each term in parentheses must be 0. And for the second term, if we set this equal to 0 and solve for a naught, we get this expression. And that may not look immediately familiar, but if you look back to the notes on the Bohr model, that's exactly the Bohr result for the Bohr radius a naught, okay, that came out of the Bohr model. So we've made a connection between the Schrödinger equation and the earlier quantum model of the Bohr model. And when the first term is set equal to 0, we just solve for e, we get the following, and that turns out to be minus some constant E0, which is the energy for the L equals 0 state. And that agrees with the Bohr, turns out to agree with the Bohr result for the ground state of the hydrogen atom. If you calculate this out, it turns out to be minus 13.6 electron volts. Okay? So just to summarize, we've applied the the time-independent Schrödinger equation to the hydrogen atom. We had to do it in 3 dimensions and in spherical coordinates as opposed to the 1 dimension and Cartesian coordinates for our 1-dimensional infinite square well. And we found that we could separate variables into 3 parts: a radial part, an angular part, and an azimuthal part. And we found that the differential equations for each of those and the boundary conditions set up quantum numbers, which we called n, nl, and m sub l. And so now we can write down the wave functions, and from the wave functions we can get the we know how to get the probability as just the wave function squared, or technically psi star times psi. Okay? So we'll be looking more at these quantum numbers and the rules, that the values that they can take, that they're allowed to take in the next lecture. All right, thanks for your attention, and see you in class.